I visited Paris in July 2014 and took some photos. This, of course, you know, is the Eiffel Tower, right? The name of Joseph Louis Lagrange appears on the Eiffel Tower alongside other French greats such as Poncelet, Boisse, Bélanger, Cuvier, and so on. I actually also visited where Lagrange is buried in Paris. So this, he is a count. If you see the text kind of over right here, Comte. Let's see. Yeah, Count José Louis Lagrange is buried in the Pantheon in Paris alongside Voltaire, Braille, as in, you know, the Braille alphabet, Antoine de Saint-Exupéry, Marie Curie, and Pierre Curie. And here's the thing, he wasn't French. So he was born Giuseppe Luigi Lagranzia in Italy. And Lagranzia moved from Berlin to Paris at the age of 51. And his students could actually complain that they couldn't understand his teaching when he spoke in French due to his thick Italian accent. Okay, let's look at the method, though, that is attributed to Lagrange. So let's maximize f of x comma y equals 4x plus 6y minus 1, subject to the following constraint. So 2x squared plus y squared minus 1 equals 0. So f of x comma y is given. G of x comma y could very well just be 2x squared plus y squared minus 1. Right, so that's what we set g of x comma y to be to fit our framework, because g of x comma y has to equal some constant. We'll compute gradients. We'll set equal after introducing a lambda, and when we set components equal, we get 4 equals 4 lambda x and 6 equals 2 lambda y. Note that lambda can't equal 0. The reason that lambda can't be 0 is because in, say, for instance, the first equation, if lambda were 0, you'd just get 4 equals 0, and that's impossible. I think for these problems, it's actually always a good idea to be very deliberate with algebra practice and just make sure before you try to divide by something on both sides that it can't be 0. Right? So since lambda is not 0, we can divide by lambda on both sides. And we're going to now get from this, you know, x equals 1 over lambda and y is equal to 3 over lambda. If we now plug those things back into the constraint equation, we get 2 times 1 over lambda squared plus 3 over lambda quantity squared is equal to 1. And that's an equation in one variable. You work this out, you get 11 over lambda squared is equal to 1. So eventually lambda is equal to plus or minus root 11. So sorry for not showing all the algebra steps, but it just kind of gets to be much. So there's two values of lambda, right? Plus root 11 and minus root 11. With the first value of lambda, positive root 11, then x and y would be 1 over root 11 and 3 over root 11. So then, yeah, from here, let's compute the value of f. So plug in this x and y into the original function f, and you get 22 over root 11 minus a 1. And if we use the other value of lambda, then you have x and y being negative 1 over root 11 and negative 3 over root 11, and plug into f, and you'll get this value here. Without even using a calculator, I think you can see that the bigger value should be with the one that starts with a fraction 22 over root 11 instead of negative 22 over root 11, right? So we can see when f is largest, it's at 1 over root 11 comma 3 over root 11. So while some algebra steps here and there were skipped on this slide, all of this was really computed by hand for this example. Okay, this number lambda that you see, lambda is the Greek letter L. It is called a Lagrange multiplier, named after Joseph Louis Lagrange. And Lagrange comes from the French version of Lagranzia. The word multiplier we use, right, because of the scalar multiple. So I hope that helps explain sort of the name of the method.